We're starting a new chapter, and actually, we're starting a new whole section that's going to be on electricity. But before we actually get into electricity as a form of energy, we need to have a conversation about electric force. We haven't done forces for a little while, so we're going to be drawing back for some things from this first semester, and hopefully they'll come back to you pretty easily and you'll be able to apply what we already know about forces to specifically electric force. You're going to find that there's a big overlap between electric force and gravitational force. They're both action at a distance forces, and they both behave very similarly with the factors that influence them. All right, so let's just go ahead and jump into this. The introduction is going to be, remember that force is a push or pull, and it is a vector quantity, so it cannot be combined by ordinary algebraic means. And you remember how we combined forces? We did it by the component method using trig to be able to pull all the components together to make a nice resultant that is actually the hypotenuse of the triangle. By the way, I'm doing it this way just because if I write more slowly, then you may be waiting for me to finish writing it. Also, my hand is in the way a lot of times when I'm writing it, and so I figured this would be good for you. You can pause the video to get it, to give yourself time to be able to finish it up. But I'm going to try it this way. The videos will be shorter. Hopefully, it'll be less of a burden to you. All right, first thing I want to talk to you about is charge. What is it? What's really unique about charge is if I asked you to define what is a negative charge, it is something that is an essential nature of something else and of an object, and you can't really define it. It can be described, but it's difficult to define it by saying a negative charge is this. So instead, we define it by its effects, what happens with it and because of it when it's around other charges, or the influence that it has on an area around it. And we'll be talking about that in terms of electric field, the influenced area around an electric charge later in the chapter. But to define a charge, you really have to define it by what happens with it and what happens because of it. And we're going to do a real quick review of the atom. I think you probably know all this stuff already, but just let's pull it to the forefront here. So the first thing that I want you to be thinking about is just what does it look like? Obviously, I have a nucleus in the center with protons and neutrons, so the net effective charge of the nucleus is going to be positive. I have electrons in the space surrounding the nucleus, and they come and go pretty easily. They're not as attached to the atom as the protons and neutrons are. Some come and go more easily than others, depending on if it's a conductor. And if it pulls electrons in, it's negative. If it gives electrons away, it's going to be positive. All right, basics of an atom just in terms of what pieces are there and the charges they have, because at this point, that's really all that we care about. All right, so the interactions of the charges, you know these already, but we'll just go ahead and run through them. Like charges repel and unlike charges attract, or like repel, unlike opposites. You can say that opposite charges attract. That's kind of comfortable and familiar to you. Like repel, opposites attract. So essentially what I'm saying is if I have a positive and a positive, they're going to repel. If I have a negative and a negative, they're going to repel. But if I have unlike charges, positive and negative, they're going to attract each other. Now, the units for charge, and this is going to be a hard thing to break because you're accustomed to the units for charge being, well, let's see. An electron is -1, a proton is +1, so we'll just call it plus or minus 1. That's chemistry, that's not physics. And it works for chemistry because it's all comparative. It's all relative to how many of one thing do you have the other. So compared to the number of protons, if I have one more electron, I have one more negative. So they call it a -1. But it's not an actual charge. It's just a relationship between how many electrons to how many protons. we actually quantify the charge. And the charges are measured in coulombs, which has the symbol of C. Let me say that again. This is not chemistry. And an electron has a charge of a negative 1.6 times 10 to the negative 16 coulombs. That's something you're going to want to remember. An electron is a negative 1.6 times 10 to the negative 19 coulombs. And a proton is going to be given the symbol in your homework. It's going to be given the symbol of a plus E. Instead of a P positive, it's a plus E. So be familiar with that. Electron, negative E, proton, positive E. And it's given the same charge, but just a different sign on it, same quantity. So it's a positive 1.6 times 10 to the negative 19 coulombs. So you can see that they offset each other. If I have an electron and a proton, I'm going to end up with something that's neutral if I have them both. All right, so this is not chemistry. Remember that. For us, a proton does not equal negative or positive 1, and an electron does not equal negative 1. A proton is positive 1.6 times 10 to the negative 19. An electron is a negative 1.6 times 10 to the negative 19. So just kind of readjust your thinking to accommodate that for physics. Okay, to pull together the relationships of these charges, what kind of force they actually create with each other, the push or the pull. The push if they're like charges, the pull if they're unlike charges. To quantify what this force actually is, we have Coulomb's law. Coulomb's law quantifies electric force. Here are the factors, and you could probably work through this in your mind. The factors are the charges, both positive and negative, so both sign and magnitude go into working through the charges with it. So the factors are the charges, and the other factor is the distance. Now, what do you think the relationship is between between force and charges? Directly or indirectly related? They are directly related. As I increase the force, as I increase the charges, I increase the force. This is F sub Q is directly related to the product of the two charges, Q1 times Q2. So as I increase the charges, both or either, it doesn't matter, I increase the force. The next relationship would be an inverse relationship. As I increase the distance squared, I increase the force. So this looks a lot like our formula for gravitational force. And pull them all together, F sub Q is directly related to Q1, Q2, and inversely related to R squared. Boy, to me, that does not look crisp. That looks a little better. All right, and you know what I'm going to say next. You can convert a proportionality into an equality by the inclusion of a constant. So that's what we're going to do next. And the constant is K. So F sub Q is equal to KQ1, Q2 all over R squared. K is 9 times 10 to the 9th newtons times meter squared over Coulomb squared. Work through why it has to be Newton times meter squared over Coulomb squared. Where do those units come from for my constant? You'll notice that for my equation up here, I have to end up with Newton, so I need to have a Newton in there. My meter squared is in the numerator, or is in the denominator, sorry. So to get rid of it, I have to put it in the numerator. My Coulomb squared is going to be in the numerator, so to cancel it out, it has to be in the denominator. 9 times 10 to the 9th, you're going to use that every time you use this equation for force. And let's just move this up a little bit. Remember that force is a vector and direction counts. Direction matters. You always have to take direction into account, and direction has to be a part of your answer. If you have a force quantity, it has to be a part of your answer. Now, it may be something as simple as they repel each other. Okay, I know what direction they're going. They're going apart from each other. Or they attract. I know that they're moving towards each other. I know the direction that they're moving. All right, let's work through a problem using F sub Q is equal to KQ1, Q2 over R squared. So the example is A woman accumulates a charge, Q1, of 6 times 10 to the 6th Coulomb while sliding out the front seat of her car. Her boyfriend has been standing in the wind and has gained electrons and now has a charge, Q2, of negative 2 times 10 to the 6th Coulomb. Calculate the magnitude of the force between them if they are separated by 0.5 meters. Is the force attractive or repulsive? Now, something that is important to say with this and make a big deal. In fact, I've got it written down here. So note that signs are not included in the problem. Let me say that again. Signs are not included in the problem. What you need to do is look at the signs and identify what direction they're going to go. They're going to go toward each other. They're going to go away from each other. You look at the signs and you identify where they're going to go. That is how I accommodate the fact that it's a vector, by looking at the relationship of the signs, alike or unlike, and what will happen because of that. All right, so let's go ahead and put the knowns and unknowns in here. Q1 is 6 times 10 to the negative 6 Coulomb. Q2, and you'll notice I put that negative in parentheses because we don't use it. So it's really, in the problem, it's going to be 2 times 10 to the negative 6, but in reality it has a negative sign in front of it. Do not put the negatives in the problems. And then the distance is 0.5 meters. I'll tell you this, which I told you when you were doing the gravitational formula. It's super easy to forget to square the R. I see that all the time. So I would just encourage you to put a big circle around that square so that you would remember, oh yeah, I gotta square that thing. Put a circle around your square so you remember you need to square it. When you do the math, you're going to end up finding that it was 0.432 newtons and the direction is toward each other. Again, if you have not already written this down, please write it down. Note that signs are not included in the formula. You won't tell me a positive or a negative newtons. You tell me the direction here. The signs are, direction matters, and the signs count with this in that it tells you the direction that it's going to go. All right, now your homework tonight is going to be 1 through 9. A couple of things that you're going to want to know through this. First of all, remember that you're never doing the questions that are on there. You're always jumping down to the bottom where it says problems. So the top part of that first page is not what you're doing. You're doing the section where it starts with the word problems. And for some of these, you're going to need to use F sub Q is equal to G M1 M, I'm sorry, F sub G, I did that wrong. F sub G is equal to, I should fix that, is equal to capital G M1 M2 over R squared. And remember that Newton's universal constant is 6.67 times 10 to the negative 11 newtons times meter squared over Coulomb squared. The other thing I would say is for the first 2 problems, it's really all about conversions. It's dimensional analysis. It probably says this in the homework, but then in the event that it does not, I will also tell you that an electron, the mass of an electron is 9.11 times 10 to the negative 31 kilograms. Again, I think that's already written in the homework, but just in case it's not, there it is. So you know the charge of an electron and you know the mass of an electron. So you ought to be able to do the conversions that you need to for 1 and 2. And then just using straight up Coulomb's formula, this formula right here is going to be the 3 through 9. All right, let me know if you need anything. This is pretty straightforward stuff as long as you remember for the first part that you're actually just doing dimensional analysis instead of using Coulomb's law. All right, let me know if you need anything.